A very good morning to all of you. Myself Deepti Jain, lecturer GPC Mohali Khulni Majra, and I am here to present a lecture on magnetic materials. First of all, let us take the introduction. What are magnetic materials? Those materials in which a state of magnetization can be induced are known as magnetic materials, or in short, these are those substances which are attracted by a magnet and that they can be made into a magnet. That is, such materials can be easily magnetized. So we can say that magnetic materials are those materials which can be easily magnetized and which can be made into a magnet. So commonly used examples are, these are the best examples of magnetic material like iron, cobalt and nickel, etc. Applications of magnetic material. If we say in the field of electrical engineering, it is used in making magnetic circuits in electrical machines, that is, it is used in generators, motors, transformers, relays and many other instruments. And in the field of electronics engineering, it is used in, these materials are used in telephones, telegraphy and many other instruments, measuring instruments. Now next is, what are the characteristics of a magnetic material? So there are number of characteristics. Let us discuss. First is magnetic permeability. Second is coercive force, magnetization curve, retentivity, hysteresis and hysteresis losses, Curie temperature, eddy current losses, demagnetization curve, magnetic field intensity, saturation constant, hardness constant and magnetization phenomena. So let us discuss each of these characteristics one by one. Now first is, what is magnetic induction or magnetic flux density? Now magnetic flux density is B, it is B. So the magnetic induction in any material is the number of lines of magnetic force passing through per unit area perpendicularly, and the units of magnetic flux density B is Weber per meter square, or it can be Tesla. Now second is magnetic field intensity. Now it is referred as H. The magnetic field intensity at any point in the magnetic field is the force experienced by any unit north pole placed at that point, and the unit is ampere per meter, or you can say that ampere turns per meter. Now next is the magnetic vectors. Now a magnetic field, either it is induced or permanent, generates a magnetic force. Now the direction of this force is drawn. Now these are represented as the blue lines. So say these blue lines represents the magnetic force. Now this is a magnet around which there are blue lines. These are the magnetic lines of force, and these represents the magnetic field. The more the magnetic lines of force, more is the strong magnetic field. The density of the field line indicates the field strength. So if the density of field lines is more, the strength of that field is very, very high. Now H is the external magnetic field. Now it is given by Ni upon L, where L is the length of the bar magnet, N is the number of turns and I is the current induced in that bar magnet. So in units of H for henries, it is also known as magnetic field strength, and it is a vector quantity. So this external field is represented as H. So this is the magnetic field intensity. Now more the magnetic lines of force, more is the density and more is the strength of that field. Now B, which is a magnetic induction or magnitude of, it represents the magnitude of internal magnetic field strength within a material exposed to an H field. So we can differentiate both H and B. So H is the external magnetic field and B is the internal magnetic field strength. Now B is represented as mu H. As you know, now B is directly proportional to H, and in order to remove the proportionality sign, we have added a mu, where mu is the permeability of the material. Now B is equals to mu H. The units of B is Tesla or Weber per meter square, and it is also known as magnetic flux density, as we have discussed in the previous slide, and it is also a vector quantity. So let us revise B and H again. So B is magnetic flux density, and it is defined for any material is the number of lines of magnetic force passing through unit area perpendicularly, and it represents the internal field strength of any material, and H represents the external field strength, and the units of H is ampere turns per meter. The next is permeability. This is very important phenomena of a magnetic material. The magnetic induction B is proportional to applied magnetic field intensity H. So B is proportional to H, and in case to remove this proportionality sign, I have added a constant here. This is mu. Now mu is known as permeability. So B is equals to mu H, and for the mu it can be written as B upon H. So you can say that the permeability is the ratio of magnetic field density to the magnetic field intensity. So if we define the mu, it can be taken as the magnetic conductivity, that is, it is the ability of a material to conduct the magnetic flux through it. So like example is the soft iron. It has the maximum permeability. So it is that property of a magnetic material which shows the ability of that material to conduct the flux. And the permeability for vacuum is, it is represented as mu naught, the permeability of vacuum or air, and it is equals to 4 pi into 10 raised to power minus 7 Henry per meter. Remember, the permeability for the free space, you can say for the vacuum or air, it is equals to 4 pi into 10 raised to power minus 7 Henry per meter. And next is the relative permeability. Relative permeability is the ratio of permeability of a medium to the permeability of a free space. It is known as relative permeability, and it is represented as mu r. So mu r is equals to, now this mu shows the permeability of any medium to the permeability of free space. So this ratio gives the relative permeability. Now mu r can be written as, now this mu is B upon H and mu naught is B naught upon H. So H cancel out. So mu r can be written as B upon B naught, where B is the magnetic flux density for any medium to the magnetic flux density for free space. The next is magnetic permeability. Now, since the permeability influences the magnetic induction, that is flux density, so it impacts how good of a magnet you can make. Means more the flux density is there, more good is the magnet, because more the flux density, more is the permeability, and that magnet will be very good. Now, in a vacuum, the permeability is a universal constant, and it is 4 pi into 10 raised to power minus 7 Henry per meter, or you can say its value is 1.27257 into 10 raised to power minus 6 Henry per meter. Now, this value can be replaced as 4 pi into 10 raised to power minus 7. So, B naught is equals to mu naught H, where mu naught is the permeability of free space and B naught is the magnetic flux density for the free space. So, let us take this example. So, here we have taken a hollow cylinder and this is a solid cylinder. So, the magnetic for the A figure, the magnetic field H as generated by a cylindrical coil is dependent on the current I. So, this is a coil. Now, it has the number of turns N and the coil length is L. Now, the magnetic flux density B naught in the presence of vacuum is equals to mu naught H, because this is a hollow cylinder. So, here we have taken the permeability mu naught, the permeability of a vacuum. This is mu naught H, where mu naught is the permeability of vacuum, which is equals to 4 pi into 10 raised to power minus 7, where H is the magnetic field intensity and it is equals to number of turns multiplied by the current. Now, for the B figure, the magnetic flux density B within a solid material is equals to mu H, where mu is the permeability of the solid material. So, this is the difference between a hollow cylinder and a solid cylinder. So, here we have taken mu naught, which is the permeability of a free space, and this mu is a permeability of a solid material. Now, next is magnetization. So, magnetization refers to the process of converting a non-magnetic material into a magnetic material. So, this material may be permanent magnetic material or it may be a induced magnetic material. So, the intensity of magnetization is directly related to the applied field H. So, M stands for the magnetization and it is directly proportional to the magnetic field intensity, that is H. So, in order to remove this proportionality sign, I have taken a constant, this is chi m H, where m is equals to chi m H and chi m H is known as magnetic susceptibility and it is equals to m upon H. So, these are the some related equations to magnetic circuits. Now, you know that we have discussed so far. Now, B is proportional to H. In order to remove this proportionality sign, we have added a constant mu, where mu is the permeability. So, B is equals to mu H. Now, mu can be written as mu naught mu r. So, B is equals to mu naught mu r H. Now, I have added mu naught H in this equation and same way I have subtracted mu naught H from this equation. So, add and subtract, add mu naught H on both sides. So, this will give B is equals to mu naught mu r H plus mu naught H minus mu naught H. So, take mu naught H common from the first and the last. So, this will give mu naught H plus mu naught H bracket start mu r minus 1. So, this H into mu r minus 1, this is magnetization, this is M. So, mu naught H plus mu naught M. Now, take mu naught common. So, this will give H plus M. So, mu naught can be written as B upon H plus M, where B is the magnetic flux density, H is the magnetic flux intensity, field intensity, and M is the magnetization. So, relative permeability, you know, mu r is equals to mu upon mu naught. Now, this will give, what is mu naught? Mu naught is B upon H plus M, and what is mu? B upon H. So, B cancel out. So, this will give mu r is equals to 1 plus M upon H. Now, 1 plus this M upon H is chi m, susceptibility. So mu r is equals to 1 plus chi m. So this is very important derivation, where we have say that this relative permeability is equals to 1 plus magnetic susceptibility, and you can say that relative permeability is very greater than magnetic susceptibility. So let us discuss some other magnetic terms again. First is relative permeability. Now it is the ratio of permeability of any medium to the permeability of the free space. So this can be written as B is equals to mu naught mu r into H. The next is magnetization. It represents the magnetic moments within a material in the presence of magnetic field of strength H. So M is the magnetization. So this can be written as B is equals to mu naught H plus mu naught M. We have derived this equation in the previous slide. So the magnitude of M is proportional to the applied field according to the magnetic susceptibility, and there are thus 4 main ways to represent B: the magnetic induction and also called the magnetic flux density. Now first B can be written as mu H. It can also be written as mu naught mu r into H. The third equation is mu naught H plus mu naught M, where M is the magnetization, and the last is B is equals to 1 plus chi m mu naught H. There are the 4 ways by which we can represent the magnetic flux density. Now the unit of magnetic flux density is Weber per meter square, or you can say Tesla. Now next slide is how do we classify magnetic properties of material, means how we classify them, whether it is a strong magnet or weak magnet. So this can be done with the help of a Faraday experiment. So this is the apparatus here you are seeing on the screen. So this is a Faraday's experiment. So this coil induces an inhomogeneous magnetic field. The sample, this is a sample which we want to discover detect whether it is a strong magnet or weak magnet. The sample is suspended from one of the arms of a sensitive balance into the magnetic field H. Now certain materials are weakly expelled from this field. Now when this sample is suspended from this arm between the magnet, now this is a magnet having north and south pole. So some of the materials, if they are weakly expelled from this field, expelled means if they are weakly repelled from this field, then these materials are referred to diamagnetic materials. So you can say that if this material is repelled by this magnetic field, then you can say that this is a diamagnetic material, and if this material is weakly attracted by this magnetic field, then this is a paramagnetic material, and if this material is strongly attracted by this field, then this material may be a ferromagnetic, it may be a antiferromagnetic, or it may be a ferrimagnetic material. So in this way we can classify, we can detect that it is a weak magnet or a strong magnet. So let us discuss the classification of magnetic material. Now magnetic materials basically are of 2 types. First is magnetic materials and second is non-magnetic material. Now magnetic materials are those which are attracted by a magnet. So examples of these magnetic materials are iron, nickel, cobalt, etc. And these materials have high permeability, whereas the non-magnetic materials are those which are not attracted by a magnet. However, when they are placed in the influence of a strong magnet, then some of them may be attracted slightly. So, again these non-magnetic materials can be classified into two types. It may be a paramagnetic materials or it may be a diamagnetic materials. So, paramagnetic materials are those magnetic materials which are weakly or slightly attracted by a strong magnetic fields, and example for this is aluminium, platinum, and for this the permeability is slightly greater than 1 and it has comparatively low value as compared to the ferromagnetic materials. The next is diamagnetic materials. These materials are repelled by a strong magnetic field, and examples of these materials are zinc, sodium chloride, and for this the permeability is less than 1. So, let us discuss all of these categories one by one. The first is diamagnetic material. So, diamagnetism is the phenomena by which the induced magnetic moment is always in the opposite direction of the applied magnetic field. Means you can say that these are those materials which are repelled by a strong magnetic field. Now, the properties of diamagnetic materials are these materials having negative susceptibility value, that is chi m is negative. Second is no permanent magnetic moment, means this is a induced magnetic material. The third is diamagnetic materials repel magnetic lines of force, means these materials always repel the magnetic field. The fourth is the value of the diamagnetic susceptibility is independent of temperature and applied magnetic field, means these materials are independent of temperature and the magnetic field. Now, examples are organic materials, alkali earth elements and bismuth. And the alkali earth elements, you can say that sodium chloride, zinc, these are the examples of diamagnetic materials. So, diamagnetic materials are those materials which are repelled by a strong magnet, and these materials have permeability less than 1. So, this is a non-magnetic material, and in the presence of external magnetic field, it represents a very weak form of magnetism. It is a non-permanent magnet and its dipoles are always opposite to the applied magnetic field. Now, this arrow H, this represents the direction of applied magnetic field, whereas the arrow in these circles, these are the magnetic dipoles. Now, these are acting opposite to the magnetic field. Now, for the magnetic material, permeability is always less than 1, approximately 0.999. It is found in all materials. Now, these materials are so weak that only noticed if no other form of magnetism exists for the atom or any crystal. The most common for atoms with completely filled orbitals. Now, these are examples are inert gases. Some ionic structures are H2O, aluminium oxide, and noble metals are zinc, copper, gold, etc. The second type is paramagnetism. Now, magnetic materials possesses significant atomic magnetic moments, often due to unpaired valence electrons. Means you can say that paramagnetic materials are those that are slightly attracted by a strong magnetic field. So, see, this is a paramagnetic material, and firstly, we have not given any magnetic field to it, so dipoles are aligned, they are randomly placed. Now when we have applied a strong magnetic field to this material, these dipoles arrange themselves in a particular direction, in the direction of applied magnetic field. So without an external magnetic field, the movements are randomly oriented. So see this diagram. Here we have not any attach the external magnetic field. So these dipoles are randomly placed. So no net microscopic magnetization. So net magnetization is 0 and it is a non-magnetic material. So once we have applied an external field to this material, the movements align with the field, thus enhancing it only a very small amount though. So when we have applied a external field to this material, these dipoles arrange themselves in the direction of applied field, but this magnetization is although very small. So for these paramagnet materials, permeability is slightly greater than 1, it is approximately 1.0001, and examples are aluminium, chromium, etc. And the third is ferromagnetic materials. So like paramagnetic materials, ferromagnetic substances possessive significant magnetic moments. Unlike paramagnetic materials, they have a significant attraction to other magnetic materials. The ferromagnetic materials have other interesting features. Now these are, unlike the atomic magnetic moments associated with paramagnetic substances, the moments in the ferromagnetic materials have strong interactions with their nearest neighbor moments. Means you can say that ferromagnetic materials are those materials which possesses strong magnetic properties, and this lead to a strong correlation between large group of magnetic moments in the ferromagnetic materials. So these large gaps are known as domains. So unlike paramagnetism with incompletely balanced orbital or spin movements which are randomly aligned, for some material unbalanced spin can lead to significant permanent magnetic moment, and these are iron, cobalt, nickel, etc. So the permanent movements are further enhanced by coupling interactions between magnetic moments of adjacent atoms, so that they tend to align even without an external field. So see, for the ferromagnetic materials, even without applying any external magnetic fields, the dipoles are aligned in the same direction. They are aligned in the same direction. So second is antiferromagnetism. So magnetic moment coupling for each individual atom does not always align constructively as for ferromagnetism. So for some materials, the alignment of the spin moments of the adjacent atom is in opposite direction. So see this diagram. In this, some of the dipoles are aligned in the upward direction and some of the dipoles are aligned in the downward direction. So with this, overall there is no net magnetic moment, even though at the atomic level there is a local movement. The next is ferrimagnetism. Are similar to ferromagnets, there is a net magnetic movement. So we have considered the three categories for the ferromagnetic materials. First is ferromagnetic, the second is antiferro, and third is ferri. Now ferromagnetic materials have a very strong net magnetic moment. For the antiferro, there is no net magnetic moment, and for the third, that is ferrimagnetism, there is a small net magnetic moment. So they are also similar to antiferromagnets because the net magnetic moment is not as large as if all the magnetic atoms coupled constructively. So the ferrimagnetism, for the ferrimagnetism, the magnetic moment lies in between the ferro and antiferro.